Nothing like starting your morning with a fresh cup of coffee and some chemistry. We are now in our last unit of class, and actually this slide is wrong. So normally we planned on covering 4 units during the fourth quarter. With some recent changes, this will be our last unit. So we've alluded to this a little bit, but you guys have learned how to calculate moles. You've learned about the different types of chemical reactions. This last word is not a typo. It is pronounced stoichiometry. A lot of times we'll call it stoic for short, and it is your last unit in chemistry. When we look at the word stoichiometry, just understanding where it comes from and its true Latin and Greek roots, stoich means element, and metry has to do with the metric system. You guys know that that's all about measuring. So what we're literally doing in this chapter is measuring elements, and what this really boils down to is real life experiments where we're going to make things in the lab and knowing how much to start with and how much we're going to produce. There's a lot of really important variables in industrial reactions that do this. Farmers have to do this, and it's probably one of the most important skills you'll ever learn as a chemistry student. So again, like we've alluded to, it is the combination of both moles and reactions. So we're mixing these two things together, and you guys are good at both of these by now, so we just have to now bring them together as one into our stoichiometry chapter. We happen to have 10 days left in the school year, so we have 10 different units, and what we're going to be doing today is converting from moles to moles. You'll see that as we go it gets a little bit harder, but we went slow enough that you can build your skills as we go. So to jump right in here, we're going to introduce this first idea. And the most important part of stoichiometry is a step called the mole ratio. It's how we convert from moles of one thing to moles of another, and it's really the fundamental step of stoichiometry. So what you guys need to understand is that when we've been writing these coefficients, they can mean a lot of different things. For every 2 particles of silver nitrate, it produces 2 molecules of nitric acid. But what those numbers truly represent are the numbers of moles, and that's what we'll use them for most often. So for every 2 moles of silver nitrate that react with 1 mole of sulfuric acid, it will make 1 mole of silver 1 sulfide and 2 moles of nitric acid. I think I break that down here. So if we look at silver nitrate to silver sulfide, that is a 2-to-1 mole ratio, because for every 2 of these, I make 1 of these. If I look at silver nitrate to nitric acid, it is also, oh, that's wrong. That should be a 2-to-2 mole ratio. There's a little typo there, my bad. We can obviously reduce that, and it's 1-to-1. If we, holy smokes, all of my stuff is wrong here. Oh, excuse me, this isn't wrong at all. An example problem would be if I had 2.5 moles of, let's say, silver nitrate right here, I know that it's half as many because of the 2-to-1 ratio. So if I have 2.5 moles of silver nitrate, I know that I would set up and make that 1.25 moles of silver sulfide because it's a 2-to-1 ratio, or it's half as much. That's just an easy example problem. Another one, if I have 2.5 moles of just a random amount, let's say, of silver nitrate, I would also make 2.5 moles of nitric acid because it's in that 1-to-1 ratio. These are your coefficients, but they're never going to be perfect like that in problems. So when you're doing stoichiometry problems, you always have to start with the chemical reaction, and it has to be balanced. If you don't balance it, nothing's going to be right. I always tell my classes to start with what you're given and write it, and then you're going to draw a bracket to help you identify where we're going, and then you're just going to be a good problem solver, and you're going to rock and roll once you have it set up. Let's do a practice problem here. So the first easy one of just identifying and going from moles to moles, this is the combustion of butane. We've done this one together. So when we go to start balancing it, I got 4 carbons over here, so I need 4 carbons over here. I know I'm going fast, but you guys know how to do this. I have 10 hydrogens on the left, so I have to have 5 waters on the right. Now if I go through and look here, that gives me 13 oxygens over here, which would make this 6.5. We know we aren't allowed to have 6.5 oxygens, so what we have to do then is double that whole reaction, and what those coefficients then become are 2, 13, 8, and 10, and now it's completely balanced. So what the problems will ask you then is we'll go identify the mole ratio. This first one would be from butane to oxygen. So I draw up my arrow from butane to oxygen. I can see that that mole ratio is for every 2 moles of butane, I'll make 13 moles of oxygen. Likewise, our next one, we go from oxygen to CO2. For every 13 moles of oxygen that I have, I will produce 8 moles of carbon dioxide. I'm sure you guys are getting the hang of this now, but if I look at the mole ratio from oxygen to water, which I can go from reactant to reactant, I can go from reactant to product, I can go from product to reactant. The one for oxygen to water is going to be 13 to 10 for the mole ratio. Butane to carbon dioxide will be for every 2 moles of butane, I can produce 8 moles of carbon dioxide. And yes, you can reduce that, but a lot of times we just keep it as is. Last one would be butane to water, and I can see for every 2 moles of butane, I can produce 10 moles of water. So always start with your reaction, draw your brackets, and then you just be a problem solver and rock and roll. Let's do one more together here, and this will be what your assignment's like. Determine how many moles of oxygen are produced by decomposing 12 moles of potassium chlorate. So I first, and sometimes you'll get the reaction, sometimes you guys have to write it, but I know potassium chlorate will decompose into potassium chloride and oxygen. Nothing is ready to go until I balance the reaction, so I'm going to go start off. I know that the question's asking me to get to moles of oxygen, so I'm just kind of making a note to myself. And then I always like to write what I'm given underneath. What I'm given is that I'm going to start with 12 moles of potassium chlorate. Make sure we're paying attention to our prefixes and our names. This is chlorate, this is chloride. So now this is what I mean by draw my bracket. I'm given moles of potassium chlorate. I want to get to moles of oxygen. So now I need to go balance it, and I kind of messed up the format there, but my coefficients would be 2 to 2 to 3. So what I go do is I always start with what I'm given. I'm just going to write down there's a 2 to 3 mole ratio. You don't have to write that, but that's my mole ratio step. I always start with what I'm given. I'm given 12 moles of potassium chlorate. I know according to my dimensional analysis that I want to cancel that out. So I don't know how I'm going to yet, but I know moles of potassium chlorate will cancel moles of potassium chlorate. So if I can, I want to get to oxygen, which is what the problem asked me to. So now I can go up, and this is where I look, and for every 2 moles of potassium chlorate that I have, I know I can produce 3 moles of oxygen. I can put these things on top and bottom because they're equivalent for this reaction. So now I remember that moles of potassium chlorate will cancel moles of potassium chlorate. All I have left now is moles of oxygen. The question asked me to solve for moles of oxygen. So now I'm done. So I take 12 times 3, I divide it by 2, and that gives me 18 moles of oxygen, which is what the question asked me to get to. So this step right here is called the mole ratio step, and the key thing is that we were in potassium chlorate. It's how we switch substances and get from one thing to the other, which is exactly what you'll do in stoichiometry. You're going to start with this, and we're going to figure out how much of this we can make. We're going to say, well, if I want to make 2 pizzas, how much dough do I have to start with? The mole ratio step, this one right here, is how you switch. It is the most important part of stoichiometry. So go get started on those. We'll do a couple more problems later.